You ever stop and wonder what's actually happening inside your phone or your laptop? It honestly feels like magic, but it's not. It's something way more elegant, really, a universal language of on and off switches. So today, let's dive into the world of digital logic and decode the secret language that powers our entire modern world.
So here's the game plan. We're going to start with the big picture, this idea of a digital world. Then we'll learn its language, which is binary. After that, we'll get into the rules of that language, meet the actual physical building blocks that use it, and finally see how all those little blocks come together to create the gadgets we use every single day.
All right, first up, we've got to wrap our heads around this fundamental illusion. The world we see and hear feels smooth, it feels continuous. But the world inside our devices, it's the complete opposite. And that brings us to the biggest question of all, right? How can a machine, just a bunch of wires and silicon, how can it possibly process information or make a decision? Well, the answer lies in making things radically simple, boiling down all the infinite complexity of our world into a language a machine can actually understand. And this right here illustrates the difference perfectly. Over on the left, you've got an analog signal. See how it's a smooth, continuous wave? That's kind of like the sound of my voice traveling through the air. But on the right, that's a digital signal. It doesn't have any in-between values. It's either on, a 1, or it's off, a 0. It's discrete, it's precise, and you know what? It's the only thing a computer really gets.
I mean, just think about it. Analog has to deal with this infinite, messy range of different values. But digital? Nah. It simplifies everything down to just two clean, distinct states, 0 or 1. And that simplicity, well, that's its superpower. So why did this simple on-off approach take over the entire world? Well, because it is incredibly effective. It's reliable because it's really hard to mistake a 1 for a 0. That makes it super fast, way cheaper to build hardware for, and a whole lot easier to program. Plus, you get a perfect identical copy every single time. That's the kind of precision you want from a machine. Okay, so we've established the what. It's all about on and off. But how does that simple concept lead to something as complex as, say, a video game or a spreadsheet? The answer is, we have to build a language using only those two states. The alphabet of this language starts with a single letter, and it's called a bit. A bit is the most fundamental piece of information you can possibly have. It's just a switch that's either off, which we represent with a 0, or on, which we represent with a 1. That's it. Everything, and I mean everything, is built from this simple idea. Now, a single bit isn't all that useful on its own, but you string them together and you can represent, well, anything. It works just like the decimal system we use every day. We all know the 1 in the number 100 is worth more than the 1 in the number 10, right? It's all about its position. Binary is the exact same idea, but each position represents a power of 2. So with just these strings of zeros and ones, we can literally build any number we can imagine. Of course, as you can imagine, representing really big numbers creates these incredibly long, dizzying strings of ones and zeros. I mean, trying to read or debug that would be a total nightmare for any human. So engineers came up with some pretty clever shorthand. And that is where other number systems come in, like octal, which is base 8, and hexadecimal, which is base 16. Just take a look at the number 15. In binary, that's 4 digits, 1111. But in hexadecimal, it's just a single character, F. See? These systems are just compact, human-friendly ways to write down the long binary codes the machine is actually using under the hood. Okay, so we have our alphabet as zeros and ones. Now we need some grammar, a set of rules that tells us how to combine them to make logical decisions. And this is where a mathematician from the 19th century comes into the picture. This guy, George Boole, developed a system of logic that, over 100 years later, would become the mathematical foundation for the entire digital age. It's an algebra that works perfectly with our binary system because it's built on just two values. You can call them true and false, or, more importantly for us, 1 and 0. And the whole thing boils down to 3 incredibly simple operations. AND is like a super strict security guard. It only outputs a 1 if input A and input B are both 1. OR is way more relaxed. It'll output a 1 if input A or input B is a 1. And then there's NOT, which is the simplest of all. It just flips the input. A 1 becomes a 0 and a 0 becomes a 1. Okay, so these rules are great, but they're just abstract math, right? How do we get a physical machine, a piece of silicon, to actually follow them? We need to build something real. And that's where the Logic Gate comes in. A logic gate is just a tiny electronic circuit that takes in one or more electrical signals, representing our ones and zeros, and it produces a single output signal based on those Boolean rules we just talked about. This chart shows the most common ones. You can see the symbol for an AND gate, an OR gate, and so on, and next to it is something called a truth table that shows you exactly what it will output for every possible combination of inputs. Now, here's a part of digital design that is just mind-bendingly cool. Among all these gates, two of them are special: NAND, which is basically not AND NOR, which is not OR. They're called universal gates, and there's a very, very powerful reason for that.
And this slide right here shows you why they are so powerful. You can construct any other logic function, and or not, you name it, using only combinations of NAND gates. The same thing is true for NOR gates. Now think about what that means. Chip designers can perfect how to manufacture just one type of block and then use it to build almost anything. It's the ultimate in design efficiency.
So, we have the language, we have the rules, and we have the physical building blocks. So now for the final step. How do we go from a single tiny gate to an entire smartphone? We connect them. Yeah, it's that simple. Look at this logic diagram. It's designed to solve a specific Boolean expression. You can see the inputs, Y and Z, are going into an AND gate. But wait, first, the Y input goes through a NOT gate. Then the output of that AND gate goes into an OR gate along with X. By wiring these simple gates together just so, we've created a more complex and specific function. Now, take that simple circuit and just imagine scaling it up. I mean, way up. A modern microprocessor doesn't have a handful of these gates. It has billions of them, all firing in perfect concert with each other. It's a level of complexity that's almost impossible to imagine, yet it's all built from those same simple and, or, and not operations. And that really is the secret. This simple, elegant system of binary logic is the bedrock of everything. From the computer you're watching this on right now, to the satellites beaming down GPS signals, to the network that delivered this explainer to you, it all comes back to simple rules applied to ones and zeros. It is an absolutely incredible story of complexity emerging from pure simplicity, which, it just leaves us with a final thought. We've used this basic toolkit to build the modern world. The only question is, what comes next?